Okay, thank you very much. First of all, thank you to Olivia and all the team for the organization of the challenge. I've done challenge in the past and it's a huge work, answer everybody and organize all these things. Well, I'm going to present a hybrid work that we did with Barry Camber. It's the title is Detecting New Multiple Sclerosis Lesion Using a Mixed Approach. I think that is not changing to, yeah, it's changing to the next slide, but slowly. Okay, then our method is based in two different approaches. One is the traditional image processing for saying something, the registration subtraction approach, plus then we add a machine learning classification algorithm to reduce the false positive and the false negative. But in what is based the traditional image processing, then it's based in a pipeline that we developed for computing atrophy that is called boundary shift integral. This pipeline we have applied in brain and spinal cord, in MS and in Alzheimer. And basically it has a lot of steps, the pipeline, to reduce the difference between the two images, because we know that despite the acquisitions theoretically are with the same scanner parameters, the look-like is different, okay? Then basically we are doing denoising, bias field correction, symmetric differential bias correction, that basically is intensity normalization, and several steps to reduce the difference between the two scans. Then this pipeline, I needed to add some priors because this is currently the pipeline that we are using in the trial office for detecting new lesions, but we are also detecting enlarging lesions. As the challenge is focusing new lesions, I needed to add priors to remove the enlarging lesions. Then I think that we can pass to Baris. Baris, are you here?
Hi, Ferran. Yeah, I am. Ferran, would you be able to switch the slides because I don't seem to have a remote control request button. So I will be talking. Well, I should say good afternoon, everyone. I'll be talking about the machine learning part of it, which is, as Ferran said, which is what we use to essentially refine the masks with from the first stage of the detection. And for machine learning, we use conventional machine learning based on a gradient boosting decision tree classifier, namely the light GBM implementation. So this was essentially a binary classification on a voxel by voxel basis, which we used. We have found it to be useful for a different line of work, and we thought it would be interesting to try and apply it to this problem. So we had a binary classification problem, and we had 3 times 7 features. So 3 is the number of inputs to the classifier. They were the 2 flares, the first time point flare and the second time point flare. And the third image was the mask from the first stage detection. And the 7 features were the essentially the in the case of the flares, the normalized flare signal intensity for the voxel of interest, and the 6 closest neighbors in 3D space. And for the BSI mask, it was the essentially the mask value for the voxel of interest and the 6 immediate neighbors. Ferran, would you be able to switch, please?
Yes,
thank you. So we used a leave on out for measuring performance, and inside that we had nested 5-fold cross validation. And following the prediction by the classifier, we performed post processing, and removed any patches, essentially any small patches, with using two criteria. One is that if the minor axis length was less than 2 voxels, we discarded the patch, or the total number of voxels was less than 3 voxels cubed. We also discarded the patches. And in our cross-validation, it seemed to improve the overall dice coefficient. And we binarized.
Small reminder, you passed already by the 5 minutes and a half, just to indicate it, sorry.
Okay, so almost finished, sorry, Michael. So yeah, so essentially we worked in M&I space, the whole thing was in M&I space. And the next slide, please. And so this is an example where you have the original images, the ground truth, which we use the consensus mask, and the first stage classification, and the improved classification using the second stage. In conclusion, our method was interesting, perhaps in that it was translated from other domains, namely atrophy and epilepsy lesion detection, using registration subtraction and machine learning together. The BSI pipeline gives efficient pre-processing for homogenizing input images, i.e. homogenizing, images from different scanners and so on. And just like many of the other teams, we use machine learning for correcting the final masks. Thank you.
So thank you a lot. Thanks a lot. So we directly, if okay for everybody, as we said, no questions. So we switch to the next presentation. So Arthur, so you can give it a go.
Arthur. Arthur, can you hear us?
Yes, I'm sorry. I had the control of the slides, so I couldn't change my mic. Can you hear me now?
Yeah, sure.
Yes.
So I'm giving you back
right.
the control.
Sorry about that.
No worries.
Yeah. Okay. So hello everybody. I am Arthur Mason, a research engineer at MPen, at INRIA in France. And I'm going to present you the method that we submitted to the challenge. So our objectives were to detect new lesions, obviously, but also to focus on detection more than on precise delineation, and to focus on patients with few new lesions. So those objectives are designed by clinicians for their own need, as Anne-Carole explained. And thank you, by the way, for your presentation. So our strategy was to adapt a method that we made earlier in our team, designed for another project, and adapt it to this task in particular. And we used the training dataset to train our model, excluding 3 patients, the 3 patients which had the largest number of lesions, and we added 53 additional patients. So overall, we had 283 new lesions in our final training dataset. And we also used external data to optimize hyperparameters, including the 3 patients with the largest number of lesions. So our pre-processing pipeline is pretty standard. We first do a reorientation, then a brain extraction, then a rigid registration, and a crop. And then finally, bias correction and 2 intensities correction steps. So the first step corrects the intensities jointly on both time steps. So the joint histograms of the 2 sequences are linearly rescaled, so they best fits the y = x line in a least square sense. And the second intensity correction step applies on both sequences separately. So it's a Nile standardization on a template. And that gives us 2 flares images from 2 time steps with a spacing of 1 times 0.5 times 0.5 millimeters, which is the median training image spacing. So we give those 2 images to a 3D UNet. We used no UNet framework, which is a framework which parameterizes automatically at the UNet. We used the standard 3D full res version, and we didn't change the default parameters, so I'm not going into the details here, but we did change the data augmentation part though. So it consists in some isotropic rescaling, some 3D rotations, some mirroring only on the sagittal plane, and intensity increase or enhancement on new lesion voxels, so to reflect the signal change of the new lesions. And the input of the UNet are patches, 64 by 160 by 192 voxel size. So we didn't change much the 3D UNet, but here you get an image, an illustration of how it's made. I'm not going into the details here. So once we have those patches, we can give them to the UNet, and it gives us a prediction, and then we can post-process the output. So the output of the softmax is a probability map that we binarize using a threshold of 0.2. Then we remove the connected component, which are too small, with a minimum volume of 4. We keep the one above 4 millimeter cube, and then we resample and resize the segmentation to the original space. So that gives us pretty good results. So here you've got a few examples from our evaluation data set. Here you can see the baseline on the left and the follow-up on the right, with segmentation obtained in red. So we have correct segmentations, as you can see here, but we also have under-segmented lesions. And we also have lesions which are detected correctly, or probably correctly. We don't know because they are not present in the ground truth. But it seems good. Thank you for your attention. That's it for our method, and see you at the poster session.
Thanks a lot, Arthur. Perfectly, 5 minutes 17. Perfect score, I would say, even on the challenge thing. No, I'm just joking. So next one, please.
So next one is.
So it's half SAIM.
Could I have the remote control, please, Olivier?
So I'm just going to give you the control over the slides. Can you try and move the slides, maybe? You may have to click on the window first.
I don't think it's working for me.
So, well, I'm going to pass the slides for you, maybe then. Oh, someone. Let's try again. I've approved your request. Yes.
Okay.
Perfect. Perfect.
Okay, so hello, my name is Jungmin Yim from Team AIM. Our team is from Korea, and I'll be giving a presentation on segmentation of new MS lesions using a multi-stage 3D patchwise deep learning algorithm. Okay. So I think because everyone today is going to be talking about multiple sclerosis, we're all familiar. Multiple sclerosis is said to be disseminated in time and space. So segmentation of new MS lesions is crucial for diagnosis and follow-up. So in this context, we proposed a method of fully automatic segmentation for new MS lesions using a multi-step algorithm. The data provided by the challenge were analyzed for number of new lesions, total volume of new lesions, and the volume of each new lesion. And out of the 40 patients for tuning data, we selected 4 patients to effectively represent the whole data. And so these figures represent the 4 patients that were selected for model tuning. The first one was one with poor registration. The second one was one where the new lesions overlapped with existing lesions. The third one was the one with the smallest volume out of those with only 1 lesion. And the last patient was one with the greatest number of new lesions. So these 4 were used for tuning, and then they were also included in the training of the model. This is the total pipeline of our process. First, we segmented the brain and spinal cord, then underwent, say, 2 streams for new MS lesion segmentation. And then the results for these 2 methods were then combined for the final output. So each data set, as we all know, consists of 2 3D flare images taken at different time points and a ground truth segmentation that were references for new lesions. First, to reduce the non-uniform bias field, N4 bias field correction was conducted for pre-processing. MS lesions are located in the brain and spinal cord, so we created a mask to exclude false positives in areas detected outside the central nervous system. For the brain mask, we used the brain extraction tool from FSL, and then the spinal cord regions were manually added by region growing from the brain mask. For training, 3D unit was used and the input data was cropped as 3D patches. The new MS lesions were segmented using the patch images of the 2 time points. Each patch was generated to contain new MS lesions, and as the input for model training, the baseline and follow-up patch images were concatenated and the provided mask was used as the ground truth. The first segmentation stage was tuned to be highly sensitive, so we added a false positive reduction stage using ResNet. The next step was segmenting the whole MS lesions from each time point using 3D unit. The labels for the candidate lesions were initially generated by the LST toolbox and then they were manually corrected. Okay, this is the final step in our method. In this step, the clusters were labeled by connected component analysis and comparison between the 2 time points were made. By comparing the results from this step, step 3, with the results of the new lesion mask from step 2, the remaining false positives were reduced and the final new lesion masks were generated. This slide represents the results for our brain and spinal cord segmentation. The model showed good results in all given data sets. And this is a summary of our new lesion segmentation results for 1 tuning data. The figures in the first line are the data provided by the challenge, and the figures in the bottom line represent our results. So false positives are reduced as each step is carried out, and the DICE score and F1 score also improve. This is another result of our tuning data. In this case also, the DICE score and F1 score improve as each step is carried out. And this is the result from 1 patient from our training data, which show similar results. So in conclusion, our method is comprised of a multi-stage CNN to reduce false positives. And thank you for listening.
Thank you a lot. Perfect timing again. Thank you very much. So we might go to Alexander Finito, who is the next.
Should be able to control the slides.
Okay, I'm trying. Do you hear me?
Very well.
Okay, nice.
Yes.
Okay. So I begin. Hello everyone, I'm Alexandre Finito. I'm a PhD student from Siemens Healthcare, and I will talk to you
Yes,
about
your
our
sound
methods.
is actually quite low.
Sorry?
We can't hear you very much.
Oh, okay. Hop. Is it better now?
Yes, perfect.
Yes.
Okay. So sorry for that. So I will present you our methods for learning a new multiple sclerosis lesion segmentation neural network.
It's gone again.
Sorry, Alexandre, it's not good now.
I can. Okay. Do you hear me now? Quite strange. The volume of my micro is just changing each time.
Or it depends. From time to time.
Avoid to move.
Yeah, I'll try to just get closer to the micro. Is it okay now?
No, not at all.
Here it's okay.
Yes, now it's okay. You have to keep in this position. Don't move.
Okay, it will be tough. Why is it? It's just moving. I don't know if it's... Okay, my bad. What's doing that? I can propose you to do the next slides and for you to do the next slides, and I try to set up things better. No?
Okay, we can try this. So let me get back to control. Can move maybe to the next one and we'll go back to this.
I have a very loud noise now.
Yeah, no, probably. All right, so let's go with the next team then.
Hello, everyone. Can you hear me?
Yeah.
Okay, great. So hi, my name is Adam Gibakar. First, I'd like to say thank you to all the organizers of this challenge. I'll be presenting on behalf of my team, IMLab from Ryerson University, Canada. And our pipeline is titled Segmentation of New Multiple Sclerosis Lesions using an ensemble of SCU nets with multi-channel patch-based inputs. So yeah, I think it's working. Great. So starting with the pipeline overview, here's the figure of our pipeline. So we propose an ensemble of 5 SCU nets to predict new MS lesions. The pipeline utilizes 4-channel patch-based inputs, which consist of time 1 and time 2 patches, as well as their corresponding attention maps, which I'll explain later. Data augmentation is applied in training, and random initialization of weights is performed for each model. And then the predictions are aggregated at the output and binarized at 0.5 for the final prediction. So in the pre-processing, ANIMA pre-processing scripts are used for brain extraction and bias field correction. And then for intensity normalization, we used Gaussian intensity normalization to increase similarity between time 1 and time 2 scans. And moreover, in the original SCUNet architecture, Gaussian intensity normalization was also used. So we wanted to be consistent with that as well. So for the attention maps, a positive difference map is computed by subtracting time 1 from time 2 and then thresholding greater than 0. This difference map is then multiplied by both time points to create sort of an attention map for each time 1 and time 2. The attention maps provide temporal differences to be learned to the model, and it also increases the amount of patches sampled. So we're able to have more patches in the training data. Moving on to the sampling strategy. So both time points and the respective attention maps are used in patch sampling, where 64 by 64 by 4 patches are sampled with 50% overlap. 64 by 64 was selected to localize small lesions while maintaining contextual information. And 50% overlap was a good trade-off between performance and computational expense. And then patches are equally sampled as positive or negative patches to deal with classic balance. So in the bottom, you can see the 4 patches that would be used as inputs. And then standard augmentations are applied during training. It's a random combination of rotation, shearing, scaling, and translation. And then moving on to the base model. So the SE-UNet model proposed by Wu et al. Is the base for this pipeline. It consists of a UNet part and a skip connection part. And the modified skip connection has been seen to help localize lesions, alleviate vanishing gradients, improve convergence, speed, and segmentation performance. Here are some of the implementation details, and the figure on the right, you can see the training and validation loss curves for each of the models in the ensemble, and we used a generalized dice loss for these models. In the preliminary results, we had a holdout set with 4 volumes with ground truths and 4 volumes without. And we were able to achieve a mean DSC of 0.73 on the holdout set that had ground truths, and an average number of false positives of 9 on the volumes that didn't have ground truths. And then on the figure on the right, you can see the ground truths on the top, and then the predicted mass on the bottom. So in conclusion, we present a method for detecting new MS lesions using ensembles of 2D patch-based units, or SE units. The use of attention maps via subtraction imaging is promising in new MS lesion detection and segmentation. And then some discussion for future work. We want to investigate different sampling strategies to include different classes of lesions, such as growing or stagnant. This will increase the number of patches sampled. And then also to implement some type of post-processing to decrease the number of false positives. And then also during development, we investigated some other types of architectures like multitask or Siamese networks to help actually learn temporal differences. Thank you. That's it for my presentation, and I hope everyone enjoys the rest of the challenge day.
Thank you a lot, Adam. Thanks a lot. And I'm not sure, maybe Alexander, if it's, could you modify or adjust your mic, or?
I'm going to approve his request. We'll have to go back a few slides then.
So do you hear me better now? I try to fix things.
So I would say we can hear you now very loudly, but it should do it. It should do it for the moment.
Okay. Is it better?
Yeah, I think we can have a try.
Let's give it a try. So I'm Alexandre Finito, and I will present you our methods for new multiple sclerosis lesion segmentation. So first of all, we perform quite small preprocessing in order to keep only the grain and to correct the field inhomogeneities. We use the Anima scripts provided by the challenge, and then to work with different resolution and different histogram, we firstly perform an histovolumetric resampling, then histogram standardization, the new methods to get all the histogram comparable, and Z normalization to have intensities around 0 in a quite small range. Then this is our architecture. This is the thing we wrote the most. Our architecture, as you can see, can be split into 2 blocks: the segmentation blocks here, this thing, and the refinement block here. The main idea behind this architecture is to first to do the segmentation of lesions with the first segmentation block, then concatenate all those segmentation and to give it to the refinement block. But because we're working with deep learning, we can't ensure this is the way how it works, but we have something that do some segmentation of multiple sclerosis lesions. The segmentation block is based on the previous work on that we performed to have a very light architecture for multiple sclerosis lesion segmentation. Our improved version have about 40,000 learnable parameters, which is quite light. We added regularizers such as batch normalization layers and dropout layers. Inspired by the Unit++ architecture, we also add deep supervision, which in fact we need multiple decoders at multiple levels of the neural network to make segmentation at different levels. Then all those segmentation are concatenated and given to the final segmentation, but also to the refinement block. This segmentation block works as a Siamese neural network because we pass first the flare image init, we get the feature maps, and then we pass the second flare image init and concatenated all feature maps to get it to the refinement block. The refinement block is a short CNN with only 4 convolutional layers and regularizers, such batch normalization layers, and 1 dropout layer. I made a mistake with the S. Then for the learning, we run on 56x56x56 batches, which were extracted mainly around new lesions, as you might see here, to avoid the problem of dealing with void patches most of the time. What you can see here is a probability map of patch extraction, so it is preferred around lesions, and yeah. The neural network has been trained around for 140 approaches with the batch dice loss, which is a dice loss computed over the whole batch instead of computed over each patches and average. Then for the inference, we take the same size of patches. We extracted them in an overlapping grid, and all patch prediction were specially averaged to get the final prediction map. This prediction map here is then resampled to the original image size and thresholded to have a binary map. So thank you for your attention. Thank you for organizing this challenge, and I'm glad to participate to it with you. Thank you.
Thank you a lot. Thanks. Perfect. So we can go on to the next presentation from Team Labrie, and it's Mr. Kamraoui.
Hi. Can you pass the slides for me, please?
I'm going to give you the control if that works for you. Just give it a try.
Okay, so hello everyone. My name is Reda. I'll be presenting our works in this challenge on the behalf of the Labrie team from Bordeaux. Okay. So the detection of new lesions is an important biomarker in multiple sclerosis that allows clinicians to diagnose, assess the evolution of the disease, and adapt the patient treatment. Recently, deep learning showed its potential when handling medical imaging automation tasks. This powerful tool seems to be suited for the complex task of predicting new lesions from 2 MRI time points. However, in order to achieve task generalization and human-like performance, deep learning-based methods require some conditions. First, such a method needs to be trained on a dataset that covers a large diversity in terms of image quality, pathology, and inter-subject variability. Second, the training process should be optimized with a loss function suited for the task of segmenting new lesions. And third, for a robust performance and to avoid overfitting, these methods should be trained with an efficient data augmentation scheme. For this challenge, we propose 3 methods. In each of them, we highlight separately one of the previous key points in the design of a proper deep learning-based method for new lesion segmentation. In our first method, we tackle the problem of the training data rarity. Indeed, in order to learn a new MS lesion, we need longitudinal data to learn the joint information contained in both time points. However, longitudinal datasets for MS are expensive and difficult to build. Our method, the Draw and Erase to Better Learn, is an innovative pipeline to simulate two realistic time points with new MS lesions from a single FLAIR scan. It is based on two models. The first one is trained for lesion imprinting, in other words, to erase lesions. And the second is trained to generate lesions. Combining both of them is intuitive and straightforward. The main idea is that from a single image, we synthesize two augmented versions. Then each version will be passed through the cascade of lesion eraser and lesion generator models in order to simulate new lesions. For instance, the three images on the right represent two synthetic time points, and the mask of new lesions is in red. In our second method, we were initially motivated to use lesion-wise detection metrics when designing the loss function. While classic metrics like DICE consider the similarity between two volumes only at the voxel level, lesion-wise metrics are computed by considering the lesions as connected components and evaluating the intersection of these sets of points between the volumes. However, due to the complexity of implementing a differentiable loss function based on such lesion-wise metrics, we propose to use convolutional neural networks to estimate these metrics. Practically speaking, we train the CNN to predict the LF1 score from two segmentation masks. Then we frisked its weight or parameters, and we used the model to optimize our new lesion segmentation model. Our total loss function is composed of a voxel-wise term we compute with DICE and a lesion-wise term we obtain from our CNN. Thus, the backpropagation updates the segmentation network by taking into consideration both voxel-wise and lesion-wise criteria. In our third method, we address the issue of MRI quality variation between the two time points and between training and testing data. In fact, the quality of images depend on several factors, such as signal-to-noise ratio, contrast to noise ratio, resolution, or slice thickness. Here, we use the image quality data augmentation, noted the IQDA. During training, we simulate on-the-flight altered version of the two time points. We randomly introduce at each iteration either blur, edge enhancement, or axial subsampling distortion. If you want to know more about our works, we invite you to the poster session. You can also contact us, and thank you.
Thank you a lot. Again, thanks. Perfect. So the next team is LIT, and Domen Preslotsnik is about to present it. And sorry for the name.
Just for a second.
Can you hear me?
Yes.
Yeah. So I'm going to give you the control now. That should work.
Yeah. Okay, before we start, I'd like to thank the organizers for giving us such a great event, and it's my pleasure to be here. As others have noted, one of the most prominent biomarkers in multiple sclerosis progression and its corresponding therapy evaluation is the ability to detect new and growing brain lesions, and this was also our motivation to research the field. Our input pipeline of our proposed method was assembled as following. Our input data was firstly reoriented to RAI Common Atlas coordinate system. We then proceeded with the Atlas registration using a priori MNI 152 Atlas image. In the next step, using a brain mask from the Atlas, we performed an intensity standardization to bring same brain parts to similar intensities amongst all images in the dataset. And finally, we did a patch extraction using predefined centers. The purpose of patch or subvolume extraction was to provide our CNN model with two inputs, one being high and the other being low resolution. The first one was extracted by cropping, while the second one was sampled by step from the original subvolume. During training, we defined 288 subvolumes, which we then augmented by reinforcing the ones containing the positive ground truth segmentation. During inference, we provide our CNN model with a much higher count of extracted subvolumes. As we see, those are over 2,300. So the two inputs, hence the name double pathway of 2 time points images, are fed into the neural network. Their feature maps are generated by passing through the convolutional blocks. Convolution blocks are usually assembled as a convolutional batch normalization and activation layer, and both pathways features are concatenated at the end. Joint features are then propagated through the fully connected pathway, which provides us with voxel classification as an output. And taking results of the fully connected pathway, we can start with our output pipeline. Output patches containing probabilities are applied to a common canvas. Meanwhile, an overlapping matrix is being assembled, and probabilities are on the canvas are then aggregated based on the overlapping generated. Then the segmentation threshold is applied, and finally the image is reoriented back to original patient space. And this is a quick recap of how the segmentation canvas is aggregated. This slide presents a single center and the next one, and the completed aggregation for all the centers, and the thresholded, therefore binary segmentation. And here are a few examples of our proposed pipeline. In the green, we see the prediction generated by our CNN model, while the red is the ground truth. And this is all for the proposed method, and thank you for your attention.
Thank you a lot as well. Thanks. So the next team will be YLE, and Mr. Shtari, if I'm not wrong, is going to present.
Yeah. Do you hear me clearly?
Yeah.
Yes. Yes.
You have the control.
Okay, perfect. Hello, everyone. First, I would like to thank all the organizers of this interesting challenge. I'm Piya Shtari, doing a PhD jointly at UCBL and KU Leuven, under the supervision of Dominique Sabi-Merenier and Sabine van Hoffel. My PhD project is part of the InspireMed Marie Curie network. I'll be presenting our proposed method called pre-activation unit. Let's briefly overview the MSSEG-2 dataset and the task. The training dataset consists of 40 scans, where for each MS patient, 2 longitudinal FLAIR images are recorded at 2 different time points. They are co-registered and manually annotated by multiple raters. The task here is to develop effective models to automatically delineate new inflammatory lesions in white matter. As shown in this example, there might be several lesions, but we are only interested in the new lesions that the patient developed between the 2 time points. The first idea came to our mind was to simply subtract 2 FLAIR images to get a useful map, but it turned out that the problem isn't nearly as simple as subtraction. This idea works in some cases, of course. For instance, in the first example, you see the subtraction map distinguishes the new lesion from the rest of the brain. But in the second one, the subtraction is not useful, mainly due to the presence of a bias field artifact in the first FLAIR image. So we ended up training an end-to-end deep model. We proposed a model called pre-unit, which has a unit style architecture with pre-activation blocks. At each stage in the encoder, the input image is downsampled by a factor of 2 using a strided convolution. And in the decoder, upsampled by a factor of 2 using transposed convolution. There are skip connections to have a better flow of the information and gradient. We also use deep supervision at the 3 highest resolutions in the decoder to further improve the gradient flow and convergence. Pre-unit has pre-activation residual block in the core where group normalization and liquid activation follow a convolution layer. The proposed model has around 26 million training parameters. Let's briefly overview some implementation details. The pre-processing includes normalizing intensity channel-wise using z-score, resampling all the images to the same voxel spacing of 0.6, and oversampling from lesion regions. We also perform data augmentation to reduce overfitting caused by data insufficiency and heterogeneity. This includes random spatial transforms and random intensity transforms. The loss is the sum of soft dice and focal loss. We use ADAM optimizer with initial learning rate of 1 to -5. And we ran the optimizer for 100K iterations with batch size 2. To make an inference for an unseen image, we took a sliding window approach with a 50% overlap. To evaluate the model, we perform a 5-fold cross-validation. The summary statistics of the scores are reported in the table. We could achieve a DICE score of around 62%, sensitivity of around 58%, and a specificity of nearly 100%. The high value for specificity and lower one for sensitivity is mainly due to the class imbalance problem. And these numbers also indicate that for many cases, the problem is more of lesion detection rather than lesion segmentation. Here some qualitative results are shown. Overall, the segmentation maps obtained by pre-unit are fairly accurate. Of course, there are also cases that the model fails to capture the new lesion. In conclusion, we devised a unit-like architecture consisting of pre-activation blocks called pre-unit for the task of new MS lesion segmentation. We successfully trained our model using data augmentation and deep supervision, mitigating the problem of data insufficiency and class imbalance. We evaluated the effectiveness of pre-unit on the MSSEG-2 dataset and achieved a DICE score of nearly 62% and sensitivity of 58% in segmenting new white matter lesions in 3D FLAIR images from an MS patient. Thank you very much for your attention.
Thank you very much for your talk. Thanks a lot. And next team is McEwen IM, and it's Corey Effort.
Yes.
Present.
Hello, can you hear me?
Yeah. Yes.
I'm just going to give the control back to you. You're there. You should have the control now.
Yes, okay, so my name is Corey, and I'm presenting our UNet pipeline for segmentation of new MS lesions. So early on, we looked at the data and saw that it's quite well co-registered, and the new lesions show up fairly well. So this motivated a fairly simple approach. We concatenate the 2 time points, and then we use a UNet. So our patch size is 96 cubed, essentially. And we concatenate the 2 time points, and we use a fairly standard UNet architecture. So our blocks are a residual block. So we use, on the main path, a convolution, batch, norm, and ReLU by 2. So we do 2 of those operations. And then on the residual path, we just use a convolution, and then we sum the outputs together. And the only unique part of our architecture, I suppose, is that we use anti-aliased strided convolutions. So it's essentially, it's a kernel size of 3 with a stride of 2, but then we apply an anti-aliasing filter afterwards. And if you look at our poster, we have a reference for that. Basically, it's a more shift equivariant pooling operation. So our loss function, we just use a mix of logistic cross entropy, and this was like the original dice loss proposed in the VNet paper. We use the squared terms in the bottom. There's no really strong evidence that not squaring it or squaring it is better, so that's what we use. Then our pre-processing pipeline. So first we use the standard like anima scripts that the organizers provided. We use bias field correction and brain extraction. And then we have a target resampling operation. So we try to get close to 1 millimeter cubed, but we have a tolerance of 0.11. So the tolerance allows us to prefer integer scaling. So we can, if like we had a sizing of 0.45, it would rescale to 0.9. So it keeps the resampling grid more aligned with the original voxels, which maybe isn't that important, but it's just something we did. Then we crop to the brain mask. We apply augmentations at training time. So our augmentations include random orientations. So we permute the dimensions, and then we also flip them. So there's 6 ways to permute the dimensions, 8 ways to flip. That gives you 48 possible patch orientations. So we just choose one of those randomly. Then we do spatial augmentations. So for that, we choose one of elastic deformation or an affine transformation. And then we do a number of intensity augmentations. So random bias field, random gamma, blur, and high frequency noise. And the final step after augmentation is intensity normalization. So we just normalize the intensities based on percentiles to the range -1 to 1. So these are a few of our training batches. So we use a batch size of 4. So this is 2 different batches. So you can see the effect of noise and the spatial augmentations. So our ensembling strategy, we train a cross-validation. So we have 5 models. And at test time, we ensemble those 5 models. And each model was trained on 32 subjects, and we hold out 8 for validation. So we also use a sliding patch window with 50% overlap. This gives 8 patches per voxel, which we ensemble, kind of averaging. And then we also do 8 flips per model. So for every single model, we flip the patch 8 different ways, pass it through, and then kind of unflip them and then ensemble them together. So this gave 320 forward passes when you combine the 5 models, 8 windows, 8 flips. So it was quite, I think it took an hour to run our models. So sorry if that was very slow, but these are our evaluation metrics. So we have a dice score. For brains without lesions, if lesions are predicted, the dice score is 0. And if no lesions are predicted, we choose a dice score of 1. And we also implemented the 2016 detection test from that paper. And this gives us precision, recall, and F1 for lesion detection. And we also trained a baseline method. So this is NNUNet. We just trained their 3D patch-based model for internal comparisons. And these are our validation results. So this is on the cross-validation. We just took the validation from each fold, and then we got all 40 subjects. So our detection F1 is 71%, and NNUNet is a bit better on that, and it's a bit better on precision, but ours is higher recall and slightly higher dice. And this is a 3D surface comparison. So on the left column is ground truth, the middle column is ours, and the right column is NNUNet. So these are the 2 subjects with the most lesions, and ours does a little bit better on these 2. Our recall is quite high, and our precision is also decent. And then these are 2 subjects that we didn't do as well on. Subject 94, I believe, has some co-registration issues. And our recall was quite high and predicted a lot of incorrect lesions here. And NNUNet handled it a little bit better, but not wonderful either. And yeah, that's my presentation. Thank you.
Thank you a lot as well for this nice presentation. And the next team will be NV Auto to present. And it should be Mr. Siddiqui if I'm not completely wrong.
Yeah, that's correct. Do you hear me?
Yes.
Okay,
great.
Awesome.
Given you the control.
Okay. I'm not sure if it's working. Okay, it's working. Okay. Hello, everyone. I'm MD Mahfouzur. First of all, I'd like to thank the organizers for such a wonderful event. And I'm going to present our solution for MS New Lesion Segmentation Challenge. So first of all, the data set overview, we had 40 training cases, 3D images, MRI images, and we had 2 images at 2 different time points. And the task was binary segmentation. We would like to categorize it that way. And we had 60 testing cases. Those were not released. So this is an overview of the data set. It's one subject with ID 13. And in our method, we actually used 2 different network architecture. Both are from MONAI, SEG-ResNet. And the first one, which one is here you can see, is a little bit a shallow version of the SEG-ResNet. It has only one downsampling shown in yellow and one upsampling shown in red. And the purple rectangle here, we call them convolutional block, and they contains batch normalization, ReLU, convolution, then again batch normalization, ReLU, and convolution operations. Our downsampling were done using strided convolution, and the upsampling was done using transpose convolution. And at the end of our network, we had this one layer, which had batch normalization, ReLU, convolution, and finally a sigmoid activations. Please note that our network has skip connections like UNet. Our second architecture was a deeper version of a SEG-ResNet. It had 3 downsampling. You can see them in yellow. And it also had 3 upsampling shown in red. You can see the purple boxes are here. It has the same operations as it had in the previous version. However, you can see in the deeper stages, we had repeated the blocks a couple more times. A little bit of training details. We used 5-fold cross-validation. As data augmentation, we applied random flip on each axis, random contrast adjustment, random brightness. And we also normalized all the inputs to have 0 mean and unit standard deviation. We used dice for our loss function as our loss function. And our input, since we had 2 network, we used a smaller input size, 16 times 16 times 16 for the shallow network, which is architecture 1, and a little bit larger patch, 128Q for the deeper network, which is architecture 2. We trained our models on 4 GPUs, each GPU optimized for batch size 512 for the shallow network, and batch size only 1 for the deeper network. As optimizer, we used add-on W with initial learning rate of 2 times 10 to the power -4, and we reduced this learning rate using cosine and link scheduler so that the learning rate becomes 0 after the final epoch. We also regularized the weight using L2 norm regularization, and we used the weight 1 to the power -5. All of our models were trained for exactly 200 epochs. We ensembled 10 models in total. 5 of them were like using the shallow network, which is architecture 1, and the other 5 were the deeper architecture. This is our 5-fold cross-validation results, which was around 0.5 dice. And that's all. Thank you very much.
Thank you a lot as well for your interesting talk. And the next team, and if I'm not completely wrong, we already met in Athens some years ago. It's Mariano Gabezas, and the team name is SNAC.
Yeah, I'm here. So first of all, thank you to the organizers. I'm not sure if it's working. Yeah, okay. So thank you to the organizers for this opportunity. I had the opportunity of participating in the first edition for lesion segmentation, and I'm happy to be here for the longitudinal one. And this time I'm presenting our approach with my team on the University of Sydney. So I'm going to be very brief. I'm going to give some background on the approach and why we decided to do that. And I'm going to highlight some of the key aspects of our approach, since the pre-processing is the common pre-processing that most everybody will use, and most of the pre-processing is also quite generic. So as you all know by now, probably, this is a highly imbalanced problem. There are just a small number of lesions and a small number of voxels that are new lesions for each patient. There is also this problem that since we have images from two different time points, there are usually differences in contrast, sometimes even differences in acquisition protocol for a few multiple reasons. And classically, in order to solve this problem, people used to use subtraction imaging between the follow-up imaging and the baseline imaging. As we've seen on one of the previous presentations, it's a nice solution, and it seems like the logical solution because it will remove any stable voxels, lesions that are in both time points. However, it is also noisy and is highly sensitive to differences in contrast. So in order to try to address these things and use this idea of subtraction, we have proposed three key elements that I'm going to explain on the following slides. So first of all, this is the architecture of our network. We use a CNN, and even if it's not completely obvious by the illustration, this is just a UNet approach. In that case, we have one decoder, but we have also two encoders that share weights, one encoder for each of the time points. Also, the other thing that we have different from a regular UNet is these circles that you can see on the network, which are attention blocks. So these attention blocks are basically just an extension of the original attention gate idea that was presented, I think, on MICCAI 2 years ago. However, we have made some slight modifications. On the original attention gate, we had the gating signal and the input features, which were coming from the encoder at different positions, so different resolutions. However, here, what we're doing is taking the features of both baseline and follow-up at the same level. Also, instead of trying to combine them and just passing them through a normal convolutional network, what we're trying to do here is to find the correlation between the features. The idea is that if there is a high correlation, either positive or negative, that means that the voxels are similar. So we don't want to keep these similarities. And if the correlation is close to zero, that means that these voxels are different. So which is the thing that we're trying to do. This is the part that gives us the tension map, where it tells the network where to focus. And on the other hand, we have the features. The features on the bottleneck come from the subtraction. Here's where we introduce subtraction again of the features between follow-up and baseline. And as we go deeper into the decoder, these features come from the previous layer. Finally, all of this relies on the idea that, so for the baseline and follow-up, we need similar features for features that stay the same, or lesions that stay the same, and different features for new lesions. But as I said, this is not always possible. So what we decided to do is to use a self-supervision approach, which is what I'm presenting here. So what we do is we take the encoder from the original network. Remember that it's just a simple encoder that we duplicate with the same weights. And we include a new decoder that has two different outputs, one for each image, one for baseline, one for follow-up. And what we try to do is to use two loss functions, one that controls the reconstruction of the images. So we try to make the final images as similar as possible to the input images. But we have a second loss that is competing against it, which is a consistency loss, which is trying to minimize the differences in features between the baseline and follow-up features on the different parts of the encoder. That way, we are trying to make the encoder find general features that are independent of the acquisition protocol. So this is everything, and thank you, everyone.
Thank you too a lot, Mariana. Thanks for having you back. And the last talk and the last team for this first time slot of presentations is Vico Rob and is Mr. Salem, who is going to present.
Could you hear me clearly?
Yeah.
Yes.
Okay. Perfect.
Given you the control normally.
Okay, thank you. Good morning, good afternoon, good evening, according to where you are. I'm going to present today MS detector, FCNN for detection of new lesions from Piya team. My name is Mustafa Salem. I'm a researcher at Piya University of Girona, Spain. Also assistant professor at Faculty of Computer and Information, Egypt, at University Egypt. First, I will talk about MS diagnosis. This is the most common diagnostic protocol which uses the McDonald's criteria and which is based on lesion dissemination in both space and time. The last version defined lesion dissemination as follows. First, dissemination in space and dissemination in time. The one that I'm focused on is a new lesion on follow-up MRI with reference to baseline scans. We have modified our previous T2 MS lesion segmentation architecture, which is published as Salem et al. In Neuroimage Clinical 2020, to adapt the requirements of the dataset provided by the MSSEG-2 challenge. The model combines intensity-based and deformation-based features with an end-to-end deep learning approach. So this is our main architecture. The input are baseline and follow-up FLAIR images. The main architecture consists of one 3D registration block and one 3D segmentation block. For each input modality, we have a registration block. In this case, we only have the FLAIR modality, so we only have one registration block. We are going to learn the deformation field, and this learned deformation field combined with baseline follow-up images are fed to the segmentation block that perform the final segmentation. So let's focus a little bit on the 3D registration block. Basically, we are based on non-registration, the classical optimization-based one, which is based on optimization problem. And this kind of registration algorithms needs to be solved for each volume pair, and it's intensive and slow in practice. On the other side, the learning-based non-registration algorithms. In this type of algorithms, a model is estimated on training data. After that, it is tested on a new data set to provide the desired results. And this enables this kind of non-registration to be combined and integrated in deep learning-based pipelines. So this is our 3D registration architecture. As you can see, it is a learning framework for the formal medical image registration. It's based on Voxomorph. It's a fully convolutional neural network that follow the U-shaped architecture. The registration block learns the deformation field and non-linearly register the baseline image to the follow-up image. We have this special transformation which warp the baseline image to the follow-up space using the learned deformation field, and this enable the end-to-end learning. Now we will focus on the 3D segmentation block. As you can see, this is our 3D segmentation block. It has two branches, and each branch is a unit. The first branch input is the FLAIR in both baseline and follow-up. The second branch input is the deformation field learned from the registration blocks. The loss functions we used in this pipeline, we have two loss functions. The first is supervised loss function, which is cross entropy. that control the segmentation part of the network. The second one is unsupervised loss function, which controls the registration part of the network. So this is enable us to make the end-to-end training. We have baseline, follow-up, and ground truth. First, the registration block try to register the baseline to the follow-up and getting the deformation field. And the deformation field, sorry, I thought, okay. And using the special transformer and the deformation field, we can wrap the baseline to the follow-up space. And then the follow-up baseline, ground truth, deformation field are fed to the segmentation block to get the segmentation mask. So we have the registration loss unsupervised, which is mean square error between the moved baseline and the follow-up image. And the second loss function is the cross entropy, which between the ground truth and the segmentation mask. For the training and implementation details, we use 3D 32 by 32 by 32 patches with a step size of 16 by 16 by 16. Extracted from the baseline.
Sorry for my interruption. Sorry for being impolite. So you passed by the 5-minute 30. Just.
Okay. This is the last slide. Sorry, this is the last one.
Oh, okay. Sorry.
Okay. A zero padding was applied. Uniform sampling of patches cover all the images. 70% of the patches used for training and 30% used for the validation. The model was trained using Adam, and the method was implemented in Python using Keras and TensorFlow backend. I'm sorry for taking a lot of time. Thank you for attention. Thank you for the organizer.